Okay. So number 5 says 12 plus 5 square root 50 minus 10 square root 98. So let's start with a prime factorization for each of these. 12 breaks down to 2 squared times 3. 50 breaks down to 2 times 5 squared. And 98 breaks down into 2 times 7 squared. We're okay there, Henry? Okay. So I have the square root of 2 squared times 3 plus 5 times 2, the square root of 2 times 5 squared, minus 10 times the square root of 2 times 7 squared. So now I'll try to simplify my radicals. I notice in the first radical I can exchange out a 2. In the second radical I can exchange out a 5. So 5 times 5 is 25. In the third radical I can exchange out the 7, and 7 times 10 is 70. So the only radicals that are identical are the square roots of 2. So those I can subtract. I can't combine those, though, with the square root of 3 because it's not an identical radical. So that square root of 3 part is just going to remain the same. And then 25 minus 70 is 45. Or negative 45, I should say. And that's my final answer there.
Alright.
Is that okay?
Yeah, I just screwed up after the simplifying part. You added, or not added, but subtracted 25%.
Cool. Julie.
You do number
6? Sure. Oh, it should be 59. There's a mistake on that one. So that number there should be negative 59. Is it? That's what you had? Yeah, okay. Yeah, so I have all the right numbers there, and then I did the arithmetic wrong somehow. That ever happened to you? Happened to me right there. Do you still need to see this? Are you okay? You're okay? Okay. Yes, thank you for asking about that one, though. I forgot to mention that. So everybody catch that on number 6, that should be negative 59. Madison. I'd love to still do 6. Yes, that's perfectly fine. I just wanted to make sure. Okay, so we'll start with prime factorizations, right? So 448. How about 2 and 224? And then maybe that's 2 and 112. And that's 2 and 56. And that's 8 and 7. And that's 2 and 4, and 4 is 2 and 2. So we have a 2 to the 6th times 7. Are you happy there, Madison? Okay, 189. That's not even, but it is divisible by 3. You know how I can tell it's divisible by 3? If you add up the digits, you get 18, and because 18 is divisible by 3, I know that 189 will be divisible by 3. That's a trick that works only with divisibility by 3, though. So be a little bit careful with how you apply that. So that gives me 3 cubed times 7. And last is 875. Since that ends in a 5, I know it definitely is divisible by 5. So I have 5 and 175. And again, ends in a 5, so I know it's divisible by 5. That's 5 and 35. And then that's 5 and 7. So I have 5 to the 3rd times 7. Are we okay to hear, Madison? Okay. Now we're going to reduce these radicals. I notice I have a 2 to the 6th inside of a cube root of 3, so I can take 2 2's out, leaving me with only the 2 2's I'm just going to write as 4, leaving me with only the 7 left. If I look here, I have a 3 to the 3rd under a cube root, so I can take both, or I take one 3 out, leaving me no 3's left, and 3 times 6 is 18. So I have just the 7 under there. Is that okay? Okay. And then same thing is going to happen with the 5's. So I can take a 5 out, leaving me with no 5's left. So that's 45 cube root 7. So if I do 4 minus 18 is negative 14, minus 45 again is negative 59. And then since they're all cube root 7's, it's just a cube root 7 at the end. So the hardest part on these is usually just the simplifying part. Once you've got it simplified down, it's just combining like terms basically and changing the coefficients, which just works just like we did for variables, right? Others from this sheet. Harley. 7. So here we have square root 140 plus square root 1260 minus square root 315. So again, going to start with the prime factorizations. 140 is maybe 10 and 14. That's 2 and 5, and then 2 and 7. So I have 2 squared times 5 times 7. 1260 is, say, 126 and 10. 10 is 2 and 5. 126 is 62 and, or I'm sorry, 63 and 2. 63 is 9 and 7, and then 9 is 3 and 3. So I have 2 squared, 3 squared, 5, and a 7. And then the 315 definitely is divisible by 5 because there's a ends in a 5. That's 5 and 63, and 63 is 7 and 9, and 9 is 3 and 3. So square root 3 squared times 5 times 7. We okay there? Okay. Now let's do our exchanges here. I can take both of these out. That'll leave me with 5 times 7, or 35. Here I can take out the 2 and the 3. So 2 times 3 is 6, leaving me with just the 5 times 7, or 35. And here I can take the 3 out, leave me with the 5 times 7, or 35. And 2 plus 6 is 8, minus 3 is 5. And they're all square roots 35, so that's my final answer. Is that okay there? Okay. Last call from this assignment. Anybody else? Okay. On to the next things here. So, Nicholas, you have...
Are you recording?
Uh-huh, I am going. Yep. I snuck it in there quick in the beginning. All right, so if you recall, we've already talked about how to multiply radicals together if they have the same index, right? So we had this rule, and it allows us to do things like the square root of 2 times the square root of 3 can be the square root of 6. What it doesn't work for is if I have the square root of 2 times the cube root of 2, it doesn't tell me what to do for this. This is what we want to figure out how to do for today. So what we're going to talk about today is how to multiply together radicals that have different indices. Everybody okay with that plan? Okay. So to do that, we're going to have to make a new definition for a radical. This new definition is going to allow us to rewrite a radical as an exponential. So this is a very important definition here. Let's do some examples of taking radicals and rewriting them as exponentials, and then exponentials and rewriting them as radicals, just so we get a good feel for how to apply this definition. So if I have the cube root of 7 to the 5th, how could I rewrite that? So the a in my case is 7. So I'm going to have a 7 over here. The m in my case is a 5. So m is going to be the numerator of the exponent. And the n in our case is 3. So the denominator of my fraction should be 3. So this is the same thing as 7 to the 5/3. Is everybody okay with how I use that? Nothing trickier than that. That's just how we use it. We can go the other direction as well. So maybe I have 5 to the 9/2. How can I rewrite that as a radical? Good. Worth noting here, do I have to write this 2 here? No. Why not? A square root has an index 2, and we don't usually write the 2 there. It's not wrong to include it, but we don't need it. Just FYI. Okay. Everybody feel comfortable with going back and forth between these two forms? Pretty easy, right? Now, the reason that we need this new definition is because we have a whole bunch of properties for exponents that we can use that make combining these things quite easy. So, properties of exponents. So if I multiply 2 exponentials together that have the same base, we add their exponents. So for example, if I have 2 squared times 2 to the 3rd, that gives me 2 to the 5th. Everybody's okay there? We've used that property a lot, right? So if I have a times b to the n, that's the same thing as a to the n times b to the n. So for example, if I have 2 times 5 to the third, that's just 2 to the third times 5 to the third. Everybody okay there? So if I have a to the m to the n, what do you suppose I'm going to do this time? I'm going to multiply the exponents. So for example, if I have 2 to the third to the fourth, that's going to be 2 to the 12th. Everybody so far so good? Okay. A to the 0 is equal to 1 as long as a is non-zero. Just as an aside, what's 0 to the 0? Not 0. It's not 1. 0 to the 0 is the exception. This is undefined. It's basically the same thing as dividing by 0. We'll show you why in a moment. So for example, say I have 3 to the 0. That's just 1, right? We've used that property before when we did the exchanges to justify like where the, when the square root just disappears or something. A to the negative n is 1 over a, again, provided that a is non-zero. So the negative sign in the exponent just makes the reciprocal. So for example, 7 to the negative 5 is just 1 over 7 to the 5th. Let's see here. And then lastly, we have a to the n over a to the m is equal to a to the n minus m. Again, provided that a is non-zero. So if I have 2 to the 5th over 2 to the 3rd, that gives me 2 to the 5 minus 3, or 2 to the 2nd. So let me just explain to you guys why something to the 0 power gives you 1, now that I have these properties down here. Well, I know 1 is the same thing as like 2 over 2, right? And 2 is really the same thing as 2 to the 1st. And if I use this property number 6, that's the same thing as 2 to the 1 minus 1, which is 2 to the 0. That's why something to the 0 power gives us 1, is because it's really basically saying it's that number divided by itself. That's kind of neat, right? Why does a negative exponent mean a reciprocal? So say like 1/2 is the same thing as 2 to the 0 over 2 to the 1st, right? Because 1 isn't something to the 0. If I use that property that we just saw, that's 2 to the 0 minus 1, which is 2 to the negative 1. Right? So we're just getting the reciprocal from the negative exponent. All right. Everybody okay with this list of properties?
Yeah.
As a fair warning, my expectation is that you will memorize this list of properties. I am asking you to do this because of the second semester topics. The one that is probably the most important moving forward is being able to apply these properties of exponents correctly and consistently. It's something that you're going to need to do many times again in all of your future math classes. It's an expectation that you'll be able to do this, like quickly and reasonably accurately. Okay? So this is an expectation that you are going to need to have these properties memorized, and not just memorized, but be able to use them fluently to kind of rearrange things to get them in a convenient form. All right. So let's look at some examples and show you how we can use these properties in conjunction with our new definition for a radical to simplify some radical expressions that we could not do beforehand. So let's say we want to multiply the square root of 2 by the cube root of 2. We could not deal with this situation previously. The reason we could not is because the index on these two radicals are different. So we couldn't use the property that just allows us to multiply the radicands together. So what we're going to do instead is we're going to rewrite these in the exponential form. So the square root of 2 has an exponent of 1 on the 2 and an index of 2 on the radical. So that becomes 2 to the 1/2. The cube root of 2 has an exponent of 1 on the radicand and an index of 3 on the radical. So that becomes 2 to the 1/3. Is everybody okay there? I can then use my first property of radicals to rewrite this as 2 to the 1/2 plus 1/3. How do I add fractions together again? What do I need to have? A common denominator. What would the common denominator be between 1/2 and 1/3? 6. How am I going to turn 1/2 to have a denominator of 6? Multiply it by 3 over 3. What am I going to have to multiply 1/3 by? 2 over 2. So that'll give me 3 over 6 plus 2 over 6. And then how do I add fractions together when they have a common denominator like that? We add the tops, but the bottom stays the same. So I'm going to have 2 to the 5/6. And then I can now rewrite this as a radical and call that the 6th root of 2 to the 5th. Or really, if you wanted to multiply it out, 2 to the 5th is 32. So you can call it the 6th root of 32 also. Either would be fine for me. You can leave them in factored form, or you can multiply them out. Sometimes some of these problems you might get something that overflows your calculator and you have to leave it in factored form, or else you're going to get some kooky number from your calculator that's in mega scientific notation that's probably not really what you'd want to write down, and just leaving it in factored form is simpler. Let's do some more. Yes? Sound good? Okay. So let's do the cube root of 12 times the 4th root of 24. Notice that this problem is a little bit different than the previous one. What's different about the previous problem? Notice that the radicands are not identical. You notice that? The previous problem, the radicands were identical. So the first thing I'd want to do here for this problem is to do a prime factorization. So the prime factorization of 12 is 2 squared times 3. And the prime factorization of 24 is 2 to the third times 3. I skipped writing down those prime factorizations because I was able to do that in my head. Are you guys okay with that? Okay. So now I'm going to use my property to convert these into exponentials. So that's 2 to the 2/3 times 3 to the 1/3 times 2 to the 3/4 times 3 to the 1/4. Is everybody okay with what I did there? I just used that definition in the very beginning to rewrite each of these as a exponential form rather than the radical form. Now, I notice that these pieces, I have some parts where the bases of the exponential are the same. You guys see that? So I can multiply the 2's together. And I can multiply the 3's together. Is everybody okay there? Can I multiply the 2's with the 3's, though? No! To use these properties of exponents, the base of the exponential must be the same. Okay? So let's continue on this. To add 2/3 and 3/4, what do we need? Common denominator. What would that common denominator be? 12. What do I need to multiply 2/3 by? 4/4. What do I have to multiply 3/4 by? 3/3. So that's going to give me 8/12 plus 9/12. If I do the same thing here, that's going to be 4/12 plus 3/12. So that's going to be 2 to the 17/12 times 3 to the 7/12. We all okay to hear? Okay. Come on in, Mr. Salek. How are you?
Good, how are you?
Good. Who are you looking for?
Indices.
Sure. Okay. Now, I could write this now in radical form. But if I look here, this is an improper fraction, 17/12, right? That's equivalent to having an unreduced radical. So I can either reduce the radical when it's radical form, or I can deal with this unreduced radical now in exponential form. We've already talked about how to reduce radicals when they're in radical form. Let's deal with this now in exponential form so you guys can see how to do that. Everybody's okay there? So the trick here with the 17/12 is I want to write this as a mixed number. So how can I rewrite 17/12 as a mixed number? So it's 1 and 5/12. You guys remember doing that in elementary school? So how many times does 12 go into 17? Once. That's the 1. How many are left over after that? 5. That's the 5. Yep. So I have an assignment here, Julie, I can hand to you right now. You're welcome. Okay. Everybody's happy here. So I just wrote that as a mixed number. I'm not done quite yet. So you guys remember this property that we used before? We've used this a bunch of times, right? I'm going to use this property to go this direction. So what is that going to allow me to do? it's going to allow me to write 2 to the first times, or that's this 2 to the 5/12, which is this one. And then I still have that 3 to the 7/12 along for the ride. Did you guys see what I did there? Notice now that all of these exponents are either whole numbers or proper fractions. Now I'm going to go ahead and reduce my radical, or I'm sorry, write this in radical form. I've already reduced. So that's 12 root of 2 to the 5th, and then the 12th root of 3 to the 7th. And since these are both 12th roots, we really could have just written this as the 12th root of 2 to the 5th times 3 to the 7th. And if you were so inclined, you could multiply that out, but that's going to be a big honking number. I'm just going to leave it in this form because, I don't know, that's going to be like 100,000 something probably, and I just am not interested in writing that down. You know what I mean? I got this answer already. That's good enough. You could, if you were so inclined, though, type that in your calculator. Everybody cool? Do I need to wait for a minute? Okay. If I get going too fast, you guys can tell me, ask me to just hold on for a second. Yeah, Caden. So this 2 here is that 2 there, which came from when I wrote it as a mixed number. So if I took 2 to the 17/12, 12th root of 2 to the 17th, because the exponent is bigger than the index, you can pull something out. Does that make sense now? Okay. So I did the same thing. I just left it in exponential form to do it. It doesn't matter to me when you pull that extra 2 out, but it's got to come out sometime. Whether you do it when it's in exponential form or when you do it when it's in radical form, it's fine. Do it whenever you want to. We'd already talked about how to do the radical form, so I wanted to do the exponential form. Does that make sense? Okay. Sorry, I know some people are still copying. I moved that on you guys. Are we ready to try another, though? Okay. All right. So, what letter are we on? C? Let's do cube root of 48 times square root of 54 over 4th root of 96. Okay. Everybody ready to rock and roll here? Guess what we're going to start with? Prime factorizations. You guys are so smart. So 48 is 2 to the 4th times 3. 54 is 2 times 3 to the 3rd. And 96 is 2 to the 5th times 3. I think I did that all right. Yeah, good. Everybody happy there? So again, I skipped drawing out the factor trees because I did those in my head. Obviously, if you have to write down the factor trees, write down the factor trees, no big deal. All right. So let's rewrite these now in exponential form. So I have 2 to the 4 thirds times 3 to the 1/3 times 2 to the 1/2 times 3 to the 3/2 over 2 to the 5/4 times 3 to the 1/4. Everybody okay there? Now I'm going to combine all the 2's together. So I'm going to have 2 to the 4 thirds plus 2 to the 1/2, and because I have the 5/4 in the denominator, I'm going to have minus 5/4. Is everybody okay with why I'm subtracting there? And I'm going to do the same thing with the 3's. So I have 3 to the 1/3 plus 3 to the 3/2. I'm sorry, plus 3/2, and then minus 1/4. We good there? Okay. To add and subtract these, what do I need to have? Common denominator. What would the common denominator be between all 3 fractions? So thirds, halves, and fourths. 12. Everybody agree with that? So if I multiply the first fraction by 4/4, I'll multiply the second fraction by 6/6, and the third fraction by 3/3. Then I'll multiply for the powers of 3, I'll multiply the first fraction by 4/4, and then the next fraction by 6/6, and then by 3/3. Oops. So that's going to give me 2 to the 7/12 times 3 to the 19/12. Is everybody okay there? Okay. Again, if you're struggling with the fractions, you can always use your calculator to do those. You guys know how to do that on your calculator? So just to show you the quick way of dealing with this, I can do 4/3 plus 1/2 minus 5/4, just using the division bar to make my fractions. And then if I press the math and the fraction command, it spits out my fraction for me. Okay? Is that all right with you guys? So that's, if you're struggling to make your common denominators and add your fractions and whatnots, that's a nice opportunity to check kind of things. All right. Next thing I'm going to do, I'm going to look at those exponents and see if any of them are improper fractions. 7/12, that's fine. 9/12 or 19/12, that's an improper fraction. So I'm going to rewrite that as a mixed number. What is 19/12 as a mixed number? 1 and 7/12. Is everybody okay with how we did that? Again, this is like elementary, middle school skill. I know it's been a long time probably since you've used it, and if you don't remember how we do it, please speak up. I'm happy to re-explain what we did there, but it should be something we remember doing, right? That's pretty standard skill. So that's going to give me a 3 to the 1st, and then I have still the 2 to the 7/12 and the 3 to the 7/12. So I'm just going to write this then as the radical 3 times the 12th root of 2 to the 7th times 3 to the 7th. And again, if you were so inclined, you could multiply 2 to the 7th times 3 to the 7th and get a number. It's going to be a big, long number, though. I'm not really interested. I will leave it in that form. And that's perfectly fine for you guys to do for me as well on homeworks or tests. Okay? You don't need to multiply those gigantic numbers out. Everybody's okay there? All right. Let's do one more example, and we'll call it good for today. Sound good? Okay to you guys? Because there's one more kind of tricky thing that can happen that we need to talk about. So let's just make sure on my end that that's going to happen. So let's do this one over this one. All right, so prime factorizations. We'll rewrite these in exponential forms. So far, so good. Okay, so that's going to be 2 to the 3/5 minus 3/2 times 3 to the 1/5 minus 3/2. To subtract these fractions, we need to have a common denominator. What's that common denominator going to be? 10. So the first fraction I'm going to multiply by 2 over 2. And the second fraction will multiply by 5 over 5. And then likewise, we'll do 2 over 2. And then 5 over 5. So that's going to give me 2 to the negative 9/10. And then 3 to the negative 13/10. Everybody okay there? Okay. So, what does a negative exponent do? So if we go back and look real quick, this was one of our properties. So the negative exponent makes a reciprocal, right? So what's that going to look like for this one? I'm going to get 1 over 2 to the 9/10 and times 3 to the 13/10. We okay there? All right. We're not done. The issue here is having these fractional exponents in our denominator is really the same as having a radical in our denominator. So we need to take care of that. So what I'm going to do, I'm going to focus on the 2's first. I want to take 2 to the 9/10 and turn it into 2 to the 1st, 2 to the 1. How many more, or what do I need to multiply 2 to the 9/10 by to get, or to turn it into 2 to the 1st? 2 to the 1/10. Everybody agree with that? So I'm going to do that to the numerator and denominator. Now I'm going to look at the 3's. What's the next whole number after 13/10? would be 2, right? Everybody agree with that? What do I have to multiply 3 to the 13th tenths by to get 3 to the 2nd? Remember, 2 is the same as 20 tenths. I'm at 13 tenths, so I need 7 tenths more. Does everybody agree with that? Are we good with that? Okay. So then I can just put this as the 10th root of 2 to the 1st times 3 to the 7th over 12. And I don't mean 12, I mean 18. 2 times 9 is 18, not 12. You ever have a dirt-to-dirt moment? Just happened to me. Okay. So let's stop here.